Alright, so in this lesson we're going to start talking about capacitance and what that really means and some ways to calculate capacitance for different types of capacitors. So the very first thing to talk about is what is a capacitor and what does it do? Capacitors, if you kind of look around in modern circuits, they're pretty much everywhere. They store charge and energy, and they can be used as both timing devices or ways to create oscillating currents depending upon how you connect them with other devices in a circuit, whether they're connected with resistors or inductors. Where this might be useful is if you have something like a digital clock, there's probably a capacitor that's a part of that circuit. If you have anything that creates a radio wave or a microwave, there's probably a capacitor in that circuit to create that radio wave or microwave. So if you were to take apart your iPhone, you are certain to find capacitors all over in there. This happens to be a very, very useful piece of electronic equipment. The picture here just shows a variety of different types of capacitors, and they are all different shapes and sizes. So what is a capacitor? What does it actually do? In the most basic sense, a capacitor contains two conducting plates, one that is positively charged, which I have represented by the blue plate here, and one that is negatively charged, represented by the red plate, separated by some type of non-conducting material. The simplest capacitor, we separate it by air, just have a metal plate separated from another metal plate by a layer of air. What this does, if we use Gauss's law, is this creates a uniform electric field between the two plates, and we can actually prove that's true. And we actually define this value C, capacitance, as the charge stored on the plates divided by the voltage across the plates, or the potential difference across the plates. So I could write the charge on the plates as capacitance times potential difference. The units of capacitance happen to be farads, and a farad is defined as a coulomb per volt. So let's look at capacitance from the perspective of Gauss's law and look at the electric field. If we defined electric field in terms of Gauss's law, the first step we do is define a Gaussian surface. And let's pick this Gaussian surface that kind of goes out over the edges of this plate a little bit. So the area that would be most interesting is really this area here, which would also be equal to the area of the plate. And so I'm just going to call that A. So I'm going to have E times A is equal to Q, the charge on this plate, divided by epsilon naught. So I could rearrange this as E is equal to Q over A epsilon naught. Now, the electric field is also interesting in between two parallel plates because it's constant, and that means if I go to calculate the electric field, there's the distance D. We would actually be integrating from 0 to D E.ds, but E is constant. It doesn't vary based upon your distance. And so if we throw that negative sign in there, plug in what E looks like, what you end up with is this relationship here, that V is equal to Q, charge on the plate, times distance between the plates, divided by area of the plates and epsilon naught. Now we defined capacitance in terms of V and Q, that it's Q over V. So if we actually take Q and divide it by this value V, we get this relationship here, which would actually be the capacitance of a parallel plate capacitor with air being between them, that it's related to the area of the plates divided by the distance between the plates and epsilon naught. So let's do a quick problem dealing with a parallel plate capacitor with a capacitance of 1 farad. So let's say we plan on making a parallel plate capacitor of 1 farad capacitance. And I want to have a plate separation of 1 centimeter, which is kind of big, but that's not all that big of a different distance. How large must the plates be to achieve this capacitance? So really we're looking for A, area. So let's solve it for area. And what I find is the area that I would need is 1.1 times 10 to the 9th square meters. As you might guess, that is ridiculously large. So a 1 farad capacitor is actually a fairly ridiculously large capacitance. We generally see capacitors given to us in the units of microfarads, nanofarads, or even picofarads. That a farad capacitor is something that is ridiculous in terms of the size of capacitor that you would have. So the second problem that I have, which is a little bit weirder, is in the figure above I have a circuit where I have switch S here. And let's say we close switch S, which is connected to an uncharged capacitor with 0.25 microfarads and a battery of 12 volts. And the lower capacitor plate we're going to say has a thickness of 0.5 centimeters, and a face area of 2 times 10 to the negative fourth meters squared. These would be pretty normal area, or pretty normal values for a capacitor. It consists of copper metal, which has a density of conducting electrons of 8.49 times 10 to the 28th electrons per cubic meter. That happens to be a lot of conductive electrons. That's why copper is a very, very good conductor, is that for every cubic meter there are a ton of electrons you have. If you converted this to moles, that's like 10,000 moles of electrons, a lot. So what we want to know is from what depth d from within the plate must the electrons move to the plate face in order to charge the capacitor. So normally what we would think of here is that this bottom plate, that this side becomes the negatively charged side, and how that actually works is that positive charges get pulled this way on the bottom plate and negative charges get pushed the other way. So let's first of all figure out how much charge needs to move in order to, well, fully charge the capacitor. And so if we do Q equals C times V, we find that 3 times 10 to the negative 6 coulombs needs to move. Second, we can figure out how many electrons this is. Convert that into number of electrons. That electron has a 1.602 times 10 to the negative 19th coulomb charge. So we find they need 1.8 times 10 to the 13th, or that's like 18 trillion electrons to move. Okay, cool. So we can actually use the fact that what electron density really is total number of electrons divided by area times distance. And it's really this distance that we're interested in here. We know the density, that's that value. I know the number, I know the area, so I can actually calculate out the distance. And we find is that electrons had to move 1.1 times 10 to the negative 12th meters, or 1.1 picometers, which seems like a really, really small distance, and it is a really, really small distance. But if you're an electron, a picometer is gigantic. If you think about what the size of an electron is, you're talking about things that are on kind of like the femtometer scale. So this would be like you walking, 10 kilometers or something like that. It's a pretty large distance compared to your size. So let's look at a couple of other different types of capacitors and what their capacitance looks like. And we're going to use Gauss's law as a way of defining those capacitors. And the first one we're going to look at is a cylindrical capacitor. These are ones that show up. What you basically have is you have some metal conductor on the inside separated by some non-conducting material by a metal on the outside. The most common type of cylindrical capacitor that I can think of is a coaxial cable. You have a metal cable on the inside, a metal cable on the outside separated by some sort of plastic or wax. So if we use Gauss's law to calculate the electric field in between these two cylinders, we'd use a cylindrical electric field. So its surface area would be 2 pi r times L, where L is the length. And so there would be our electric field. If we apply the idea that voltage is electric field dot ds, in this case the electric field does vary based on R. And so if we actually plug in everything, we get this expression for voltage if we do the calculus. Where this negative sign goes is, remember that you can get rid of the negative sign by flipping the limits of an integral. And so if we actually take Q divided by V and plug that in, we get this as a result. Kind of an interesting thing. So really the capacitance depends upon the length of the capacitor and kind of the ratio of A and B, so what this difference in distances look like. If we do a spherical capacitor, so say we had a ball inside of a spherical shell, we can use kind of our spherical geometry to figure out the electric field. We can then figure out the voltage. We've kind of done this problem before. That it looks like that. Again, we do the same, flip things around, and there's another negative sign that gets introduced because this actually becomes negative 1 over r. So that's how I get that. What I've done is I've added these two fractions by finding the common denominator a times b. So we get b over a times b, and it's a over a times b. And if we do q over v, we get that relationship there. So again, really what it's related to is just how big the two spheres are, and that's it. Now the last type of capacitor that's kind of interesting is that an isolated sphere of charge can act as a capacitor as well. And we probably already know this when we did the Van de Graaff generator demo. Essentially what we're doing is creating an isolated sphere of charge. So what I'm going to do first is rearrange this fraction a little bit. I'm going to create, basically divide B, kind of divide everything by B over B, and what happens when you do that is you get this relationship. A basically is R, the size of that little sphere, and B is infinity. We're assuming there's an outer spherical shell and an infinite distance away. What happens when you plug those values in here is A over B becomes 0, and so you end up with basically 4 pi epsilon naught times R. And so that's kind of a quick overview of capacitance and some ways to calculate capacitance. We'll look at in the next lesson is energy stored in capacitors.